Every day, new molecules come into existence. Molecules that did not exist before are created in the lab by scientists. However, the way molecules come into being is changing. Now, molecules can be created inside the chips of computer processors before they are ever made in the lab. And properties of these molecules can be known before they ever are synthesized. But before we explore these new methods of creating molecules, let's try to understand how molecules were made in the past, starting 13.8 billion years ago at the dawn of time in a world without molecules. Before there were stars, before there was light, the universe was a hot, dense sea of particles, a turbulent beginning birthed by the Big Bang. As this firestorm expanded, it began to cool, allowing the first atomic nuclei to form. This epoch, known as primordial nuclear synthesis, was the foundation of all cosmic chemistry, giving rise to the simplest elements: hydrogen, helium, and traces of lithium. But even these early building blocks bore the potential for more. At this time, it was a universe without molecules, and the first molecular bonds faced daunting challenges: intense heat, high-energy photons, and sparse environments. Yet, helium, with its unique properties, took the lead. Helium is a noble gas, reluctant, almost inert. It required exceptional conditions to interact. But when it did, it formed the universe's first molecule, helium hydride. This moment was the dawn of molecular chemistry. It was the spark that would ignite the universe's journey from simplicity to complexity, from atoms to molecules, and eventually to life itself. Helium hydride carries within it the story of the cosmos's first steps, a testament to creation in the most unlikely of places. Much richer chemistry would have to await the formation of the larger and more complex elements of the periodic table. At first glance, the periodic table offers a clean, ordered vision of these building blocks, charting their progression by atomic mass. It begins with hydrogen, helium, and lithium, the first three elements to emerge from the fiery aftermath of the Big Bang. But this story is anything but linear. The creation of elements is a tale as varied and complex as the stars that birthed them. Hydrogen and helium emerged directly from the universe's first moments, their nuclei forged in the high-energy crucible of primordial nuclear synthesis. Lithium followed, though in trace amounts. Beyond this, the story shifts from the expanding void of the early universe to the hearts of stars, where nuclear fusion took over as the master craftsman. In the cores of young stars, lighter elements like helium fused into carbon, nitrogen, and oxygen, the essential atoms of life. In larger, hotter stars, this process extended further, producing heavier elements like silicon and iron. But even the mighty stars have their limits. To create elements beyond iron, the universe required more cataclysmic events. Supernovae, stellar explosions of unimaginable power, fused and scattered the heaviest elements, seeding the cosmos with gold, uranium, and more. The cosmos is a vast cradle of molecular complexity, where molecules form through diverse mechanisms shaped by the extreme conditions of space. From cold molecular clouds to the violent outflows of dying stars, these processes add to the universe's chemical diversity. In molecular clouds, where densities are low but interactions occur, gas phase reactions dominate. Charged ions and molecules collide, forming new species. UV radiation and cosmic rays break molecular bonds, creating reactive fragments that recombine to form new compounds. Supernovae, stellar winds, and cloud collisions produce shocks that compress and heat gas, driving reactions that would otherwise be too slow in cooler environments. Near young stars, in hot molecular cores or protoplanetary disks, high temperatures enable complex organic molecules to form. molecules frozen on dust grains sublimate into the gas phase, where they continue reacting in dynamic environments. In other regions, UV light breaks molecules into smaller fragments, which recombine to sustain molecular synthesis. Meanwhile, interstellar dust grains act as catalysts, hosting reactions powered by cosmic rays or thermal processes, releasing molecules back into the gas phase as stars form. The molecular richness of space is continuously replenished by the life cycle of stars. Stellar winds and supernovae inject heavy elements into the interstellar medium, providing the raw materials for new chemical pathways. The molecules formed amongst the stars range in size from the smallest molecule, diatomic hydrogen, up to structures as large as Buckminster fullerene. However, the list of molecules detected in interstellar space number in the hundreds and represents the tiniest fraction of known molecules. The greatest molecular diversity arose not between the stars, but on planets. In the atmospheres, oceans, and on surfaces of planets, the components of new molecules could accumulate in close contact, allowing reactions to grow larger and larger molecules. For example, tholins are complex organic compounds that form when simple carbon-containing molecules like methane or carbon dioxide are exposed to high-energy radiation like ultraviolet light or cosmic rays, usually in the presence of nitrogen or water. They are commonly detected on the surface of icy bodies in the outer solar system, most notably on Saturn's moon Titan, where they create a reddish-brown haze in the atmosphere. But the greatest expansion in the molecular library of the universe required another spark, that of life. While we do not know where else life may have started, we are learning more and more about how life started on Earth. Imagine Earth 4.6 billion years ago, a seething ball of molten rock and metal, chaotic and lifeless. The young planet had no atmosphere to speak of, only the remnants of the violent collisions that formed it. Early Earth, during what we now call the Hadean Eon, was far from the life-supporting planet we know today. Its surface was a molten inferno, pummeled by cosmic debris. As Earth cooled, the molten surface began to solidify, and volcanoes roared to life, belching gases into the sky. This was the birth of Earth's first atmosphere. It wasn't the oxygen-rich air we know today, but a thick, choking brew of hydrogen sulfide, methane, and an overwhelming amount of carbon dioxide, up to 200 times more than we have now. The atmosphere was dense and toxic, a far cry from anything that could sustain life as we understand it. Liquid water began to pool across the Earth's surface, transforming the young planet. Amidst this chaotic and tumultuous environment, the seeds of life started to take root. Deep beneath the oceans, hydrothermal vents, heated by geothermal energy, may have provided the perfect crucible for the first molecules of life to form. Shielded from the harsh ultraviolet radiation and violent surface impacts, the ocean depths offered a haven for life's earliest steps. At hydrothermal vents, extreme conditions gave rise to microbial communities, thriving on the raw materials and energy these environments provided. Here, hyperthermophilic bacteria and archaea could harness the building blocks of life, setting the stage for the profound journey ahead. Even the simplest modern organisms, such as Escherichia coli, contain thousands of proteins and small molecules within their cell walls. The emergence of life marked a significant milestone in molecular history. While the first epoch of molecules was driven by chaotic cosmic processes, the history of molecules now became guided by evolution, a relentless force driving the creation of more efficient molecules to sustain and advance life. Over billions of years, new organisms emerged, bringing with them an incredible diversity of molecules. In humans alone, over 250,000 small molecules and 20,000 proteins have been identified. and humans are just one species among millions on this vibrant planet. To appreciate the scale of chemical diversity created by life, one must understand the scale of biodiversity on the planet. To estimate the scale of biodiversity, scientists turn to patterns in taxonomic hierarchies, uncovering a strikingly predictable relationship between species counts and higher taxonomic ranks. Using this method, they estimated Earth to be home to nearly 9 million species. And this is the tip of the iceberg that includes all the organisms that ever existed. While many of the simplest metabolites are common across organisms, each new species brought forth new molecules and new proteins into the universe. The origin of life on Earth, and possibly elsewhere, marked a transformative chapter in the history of molecules. Life's emergence introduced an unprecedented level of molecular complexity, giving rise to trillions of unique compounds shaped by the processes of evolution. Yet, this was not the final chapter in the story of molecules. Among the organisms that evolved on Earth, one developed an entirely new way to create molecules, heralding a third epoch in the history of molecules, one driven by human ingenuity and synthetic chemistry. The history of molecules is a story of exponential growth and discovery. In the early 19th century, chemists began systematically exploring the chemical space, the vast universe of possible molecular combinations. Early efforts focused on extracting compounds from natural sources, but by the mid-19th century, the advent of structural theory transformed chemistry. It allowed scientists to create new molecules with precision. This era was marked by a dramatic increase in the synthesis of new compounds. By 1900, over 90% of new substances were synthesized in laboratories rather than extracted from nature. The exploration of chemical space accelerated, with chemists producing an ever-expanding array of molecules. The 20th century brought even greater innovation. From the 1960s to the 1980s, the rise of organometallic chemistry opened up entirely new classes of materials. Molecules combining organic structures with metals offered new properties and applications. This period saw the synthesis of materials crucial to industries like catalysis, electronics, and energy. Today, the pace of molecular discovery is staggering. Chemists now produce millions of new compounds each year. Over 180 million molecules have been reported. Despite this explosion of diversity, a striking pattern remains. Most new compounds are built from a small subset of elements, dominated by carbon, hydrogen, nitrogen, and oxygen. As we continue to expand the molecular frontier, the story of molecules reflects humanity's unyielding drive to innovate and explore. Even with millions of compounds catalogued, the chemical space remains largely uncharted, a vast, infinite universe of possibilities, waiting to be discovered. Over 100 million molecules have been prepared in laboratories, a staggering accomplishment. Yet, this number pales in comparison to the trillions of molecules that have been created by the organisms of Earth. Still, even these represent only a tiny fraction of what is theoretically possible in the vast chemical universe. Molecules can contain any arrangement of atoms in any sequence or combination. The possibilities are so vast that for molecules with just 30 atoms, the potential combinations exceed 10 to the power 63, a number greater than the total atoms in our solar system. This sheer immensity is what scientists refer to as chemical space, a boundless frontier filled with unimaginable potential. While scientists have explored only a tiny corner of this space, the discoveries made so far are nothing short of astonishing. Penicillin revolutionized medicine. Progestins reshaped human biology. Batrachotoxin revealed the toxic ingenuity of nature. Imatinib provided a lifeline for cancer patients. Semaglutide offered a breakthrough in treating chronic disease, and compounds like lysergic acid diethylamide have shown us the profound interplay between chemistry and the mind. These molecules are just the beginning. What other wonders lie hidden in the uncharted expanse of chemical space? This exploration faces limits, and the chemical space that remains is vast beyond imagination. Yet within it may reside the next penicillin, the next revolutionary molecule that transforms our understanding of science, medicine, or technology. The challenge now is how to find it. How do we navigate this infinite sea? Traditional approaches like trial and error synthesis are limited by time and resources. Instead, researchers are turning to computational modelling and AI-driven predictions to identify promising candidates. These tools offer a glimpse into the unexplored regions of chemical space, suggesting that the next breakthrough might be closer than we think. One way that computers allow us to explore new regions of chemical space is through virtual libraries. One library, called Real Space, is comprised of 65 billion molecules. It stands as the largest collection of commercially available compounds ever assembled. These molecules have not been synthesized, and most have never existed in the universe before. Yet, before they are ever made, their properties can be calculated, and scientists can determine if they have the properties they desire. Each molecule in the real space is designed to be built using make-on-demand technology, selecting from over 167 synthesis protocols and a library of more than 170,202 high-quality reagents and building blocks. These virtual compounds are not merely hypothetical, they are readily accessible, with an average synthesis time of a few weeks and a success rate exceeding 80%. Other companies are working on even larger libraries, targeting 10 to the power 26 molecules, more than the number of stars that exist in the universe. The impact of these libraries is profound. It exemplifies the transition from traditional trial and error synthesis to a future driven by data, algorithms, and automation. By making an almost unimaginable number of compounds searchable and accessible, the real space has the potential to revolutionize fields ranging from pharmacology to materials engineering, ushering in a new era of molecular innovation. Recent studies show that as library size increases, so does the quality of molecule binding to its intended target. The tangible impact of ultra-large libraries is clear. They have significantly broadened the chemical diversity accessible for testing, often exceeding the performance of libraries containing only molecules that already exist. Yet, an intriguing shift accompanies this expansion. As libraries grow, their resemblance to bio-like molecules, compounds that mimic metabolites and natural products, diminishes. This opens the door to entirely new molecular architectures that evolution has yet to explore. Another area where computers are accelerating our search for novel molecules is using artificial intelligence to imagine and create entirely new molecules. This field of generative chemistry is a groundbreaking new chapter in science. Using AI-powered tools like generative adversarial networks and reinforcement learning, we can explore chemical space in ways that were previously impossible. Imagine an artist creating a masterpiece by blending elements from nature and their imagination. This is essentially what these AI systems do. They analyze massive data sets of known molecules and learn the rules of chemistry. Then, using these rules, they dream up new molecular structures that fit specific goals, like fighting diseases or creating stronger materials. The potential here is vast. Chemical space is unimaginably large, and finding useful molecules in this enormous haystack is the challenge. This is where AI shines. By simulating and scoring billions of molecules virtually, AI tools can narrow down the search to compounds that are likely to work in the real world. For example, generative adversarial networks have been used to design molecules targeting diseases like cancer, malaria, and bacterial infections. Reinforcement learning has enabled the creation of compounds with specific traits, such as improved solubility or reduced toxicity. Some of these molecules have even been synthesized and tested in labs, showing promising results. The story of molecules is far from over. In fact, it is accelerating into uncharted territories. From the earliest cosmic chemistry to the complex molecular networks of life, the history of molecules has been one of boundless growth and discovery. But today, we stand at the edge of a new era, one where human ingenuity and artificial intelligence are reshaping how we explore the molecular universe. Through virtual libraries containing billions of molecules, scientists are not only cataloguing possibilities, but transforming them into reality. Molecules that have never existed before can now be designed, assessed for their properties, and synthesized within weeks. This shift from discovery to creation is expanding chemical space in directions evolution never ventured. At the same time, AI-driven generative chemistry offers a bold new frontier, where machines imagine molecules that fit specific goals, from curing diseases to building advanced materials. These tools, capable of navigating chemical space at lightning speed, promise breakthroughs that were once thought impossible. The vastness of chemical space remains an infinite frontier. Yet, as we combine the power of computation, automation, and creativity, we are beginning to illuminate the hidden wonders it holds. What lies ahead may redefine the limits of science, medicine, and technology, marking the next epoch in the extraordinary history of molecules.